So we're going to continue with our discussion about RxJava and some of its operators in the observable and flowable and single classes. We'll start out by talking about some of a suppressing operator. And you'll see that suppressing operators are used to change or ignore portions of the payload in a stream, in a flow or a stream with RxJava. And we're going to talk about the filter operator. So this operator is going to be used to evaluate some value that's being emitted, or a sequence of values that are being emitted from the observable before it, and then check to see whether or not those values match a given predicate, where a predicate is essentially one of the interfaces that's defined in Java. It's a Java functional interface. Note, by the way, that RxJava was designed to work with versions of Java prior to Java 8. So as a consequence, it couldn't rely on the function package existing, so it defines its own function package with functional interfaces like predicate and consumer and function that are very similar, if not identical, to the ones you get with regular Java 8 and beyond. If the predicate test succeeds, then the value will be emitted by the observable. Otherwise, if it fails, the value will be ignored and a request is made upstream to provide another element. By the way, almost everything I'll be talking about here applies both to observable as well as to flowable. And so I use observable in some cases, but be aware that your programming assignment uses flowable, but the methods also, the operators are also there as well. What you get back when you filter an observable that's upstream or up the chain is a new observable that contains only values that pass the predicate test, which should be pretty obvious. As a consequence of this, if there are things that don't pass the test, the number of items that will be emitted may be less than the number of input elements. And so as you can see here, it's an example where we're going to emit a bunch of integers that'll be random, and we're going to go ahead and only allow odd numbers to go through this particular stream or flow. And you can take a look at this in this particular example from my reactive folder in my GitHub repository. Note that filter cannot change the type or values of the elements that it is processing or filtering. It can only let them flow through or not, so no changes are allowed. Project Reactor has a filter operator that works in exactly the same way, with exactly the same purpose, with exactly the same result. No surprise, Java Streams also has a filter operation that we've seen before that also does the same thing. So this is another example of only emitting odd numbers. So that's just a quick overview of a suppressing operator that you're going to need in order to be able to do assignment number 5. Let's move on and talk about some other transforming operators, some very interesting transforming operators. And this will be one called flatMap, which, as we'll see, will transform the values and or the types that an observable or a flowable can emit. So let's talk about flatMap. At first glance, this looks quite a bit like the map operator, and we'll actually compare and contrast them specifically in just a bit. What this operator does is it transforms the elements that are emitted by the observable asynchronously. It doesn't always have to be done asynchronously, but that's a very common way to do things. The items that are emitted are based on applying a function to each item that's emitted by the observable that's upstream. This is a mapper function. Again, this is why this looks so much like map, because there's a mapper. And the function returns an observable source. And an observable source is a type of element or object or data that can be consumed by an observer. And what happens is that the observable sources that are returned from this mapper are merged together, and the results of this merger are then flattened and emitted. So I always like to visualize a steamroller coming along and flattening things out. Therefore, if you've got different elements, they can interleave with each other. So when you flat map the sources, you can have them interleave. You can have one element return 2 elements, and then you can have one element return elements, and those elements can interleave based on various properties, primarily whether concurrency is being done or not. As a consequence of all this, the number of output elements may differ from the number of input elements, and this is what makes flatMap different from map. Remember, map can always must have a one-to-one correspondence between input and output. unless an exception occurs. Whereas with flatMap, you can have multiple elements or no elements come out. So you can have greater than, less than, or equal to as the output. Also, like map, flatMap can transform values or the types of the elements that it processes. So you can see here we went from one type, which is denoted by a circle, to a different type denoted by a diamond. We typically use this operator when we're going to trigger concurrent processing. And we're not going to spend a lot of time talking about this because we're going to use a different way of doing concurrency using something called a ParallelFlowable, but I want you to at least be aware of this particular idiom. It's called the flatMap concurrency idiom. And basically the way this works is flatMap will take each element that's emitted to it from the observable upstream, and for each element, it will then go ahead and do something that will cause that element to be processed in a different thread in a pool of threads. So in this particular example, we're going to take a bunch of big fractions, and each of those big fractions will then be multiplied concurrently in the computation thread pool. And so this basically, you can think of this as a way of starting a bunch of asynchronous computations running concurrently in the scheduler's pool. And then when it's all done, it'll take the results of all that and reduce it by adding them all together. So that's one way of being able to get concurrent execution with RxJava is by using the flatMap concurrency idiom. And as you might expect, because all these operations are running concurrently, that's a circumstance under which they tend to interleave. So that's one way to do things. I find that a little complicated, so we're actually going to use a more straightforward approach for the programming assignment, which we'll talk about in a bit. Project Reactor has a flatMap operator that works essentially the same way that RxJava's does. And Java Streams also has a flatMap operation that we've talked about before, which can be used in much the same way to flatten out data structures and basically pull apart nesting so things end up being streamed in a more linear way, if you will. The key thing to remember is that flatMap in Java Streams does not support parallelism effectively for all the reasons we've talked about throughout the course, which is why we have to use stuff like map multi in parallel streams to get the behavior that will run concurrently. In contrast, flatMap in Project Reactor's Flux and RxJava's Observable and Flowable can support parallelism. So it does not have that wacky limitation that we have with Java Streams. Keep in mind that flatMap doesn't ensure the order of the items in the resulting stream. They can interleave. If that's a problem, you should consider using concatMap. And concatMap will obey or maintain this ordering, which may or may not matter. Usually doesn't matter, but if it does matter, you can use concatMap. So let's compare and contrast map and flatMap in the context of observable. Keep in mind it's the same thing for flowable as well. So let's take a look at these two operators and have them duke it out. So map takes each value in an observable that is used to generate or emit values, and it will map each value into a single value. So you can see here there's a one-to-one correspondence with input and output. So it's typically used for so-called synchronous one-to-one transformations, where the number of output elements is equal to the number of input elements. In contrast, flatMap transforms each item in an observable or flowable stream into an arbitrary number of values, 0 or more. So it might do less, it could do the same, it could do more. Usually it does more, but it can do less. And as you can see here, that's one of the major differences. The other major difference is that it's intended for asynchronous 1 to n transformations, where one item goes to n, which could be 0. So as a result, the number of output elements may differ from the number of input elements. And oftentimes it's done concurrently, so you get the asynchronous nature as well. flatMap is very popular in RxJava. You'll use it a lot. It's often used in ways where you might think you can use map, but when you play around with it, you really realize you have to use flatMap. We're not going to use flatMap a whole lot in our programming assignment because we're going to be using ParallelFlowables instead, but just be aware that that is a common way to do things in RxJava. So that's another transforming operator. So now you know about map and flatMap. You'll need to know both of those in order to do programming assignment number 5. So now let's talk about error handling. Error handling in RxJava with both observables and flowables is very similar to error handling in Java completable futures in the sense that there are certain operators that are inserted into a chain of operators, and when an exception occurs, the flow of control propagates to the appropriate error handling operator rather than going through the intermediate operators that are being skipped because an error has occurred. So let's take a look and see how this works. And we're going to talk about the on-error return item example. So on-error return item is an operator that ends the flow with the given item when the observable fails. And it does this rather than signaling an exception or an error using the on-error operator, or on-error hook method, sorry. And the value parameter here, this item, will be emitted via a regular onComplete when an exception occurs. And that will then traverse up the chain further. This returns an observable that will emit the given item. So the item will be emitted at that point, and then the stream will terminate. What's important, or that operator terminates. What's important here to realize is that the on-error return item operator swallows the exception, so it doesn't propagate any further up the call chain or the call stack. That's commonly known as error hiding. Sometimes a good thing, sometimes a bad thing, but it's a thing, so you have to be familiar with how it works. Here's a simple example that you can play around with if you take a look at this EX3 case study in my reactive observables folder in my live lessons GitHub repository. And what this does is it's going to take an observable that will create a value, a big fraction value that is going to have a denominator that might be 0. If the denominator is 0, of course, it'll blow up because it'll end up getting the arithmetic exception error. In that case, the flow of control at that point will transfer to the on-error return item operator, and that will simply return 0. Not necessarily the best way to handle things, but it's a way to handle things, and you'll have to be familiar with this approach in programming assignment number 5 in the perform crawl method, because you're going to have to handle errors there, and this is how you're going to handle it. You won't return big fraction 0, but you'll return the appropriate value. Project Reactor has a flux on-error return operator that works the same as on-error return item. They overload it so it can take different parameters, so it's a little bit more consistent in Project Reactor. In general, you'll find that Project Reactor is a little bit more coherent than RxJava. It had the benefit of coming later so people could address things in a more coherent way and more consistent way. The exceptionally method in Java completable future is very similar to on-error return and on-error return item in these reactive streams frameworks. There's lots of other stuff about error handling. There's other ways of dealing with things. There's something called on-error return next. There's something called on-error resume, and so on and so forth. We aren't going to talk about those right now. We're just talking about this one example because you need to know how to do it for the assignment. We may have time later to come back and look at these things in more detail. Next topic I'd like to talk about actually is a little different from what we've discussed so far, because unlike the other operators which dealt with observables and/or flowables, this is going to work on singles. So as you may recall from our earlier discussion a week or so ago, single is basically a class that's going to emit a single value or an error will occur. And one of the things you often need to do is have one place in your program where you block waiting for something to emit a value. And to do that, you use the blocking get method on a single. And this single typically emits a value that usually has been produced or emitted from something running in another thread of control. So you usually block one thread while other computation is taking place asynchronously, which is exactly how your programming assignment works. You start all these recursive web crawls, and you have the main thread wait for them to finish. So let's talk about blocking get. So what this does, it'll block until the single that it's called upon signals a success value or an exception. And when it succeeds, when an exception is not thrown, it returns the value that it received. If something goes wrong, then an exception is thrown, whatever the original exception was that came from whatever source was having the issue. And these exceptions are wrapped up as runtime exceptions. which is a nice thing because checked exceptions are a royal pain with Java, especially when used in functional or reactive programming. Oddly enough, there is no timed version of blocking get. Instead, there are timeout operators that you can use in order to handle timeouts in a slightly different way. We're not going to talk about timeouts here. If we have time, either at the end of today's class or next class, I'll show you a case study that illustrates how to use timeouts. They're actually pretty cool. Internally, blocking get calls the subscribe operator to initiate the processing chain. We haven't really talked a lot about subscribe. When we're done giving the overview of what you need to do the programming assignment, we'll go back and talk about subscribe. Subscribe is what's used to initiate the processing in an observable or a flowable. And as you'll see, remember, these are lazy until subscribe is called. And the way that blocking get works, if you look at the source code underneath here, you'll find that blocking get works by creating something called a blocking multi-observer, and then subscribing to it, and then waiting on that for the computation to finish running in the background, whatever it's doing. So that's what's happening under the hood. So it's always the case that subscribe has to be called. It's what's called a terminal operator, much like collect or reduce or some of the other things like for each are in Java streams. By default, the blocking get operator doesn't run on a particular scheduler. It's going to borrow whatever thread it was called from, which is usually could be the main thread or the UI thread or some other thread, not usually the UI thread. It's usually some thread that wants to block. And as I mentioned before, what actually emits the value that blocking get waits on is usually running asynchronously in a totally different thread of control. You usually limit the use of blocking get to parts of your program where you absolutely positively must wait synchronously for asynchronous computations to complete. So here's a simple example where we're going to emit some value. We're going to have this thing run in the background somewhere, and we're going to wait for it to finish before we continue. Really want to limit this to just one place in your program if you possibly can. Project Reactor has a mono class, which is very similar to single, and it has a block optional method, which is very similar to block, and it'll block indefinitely until a signal is received or the mono completes with an empty value, which means it didn't succeed for whatever reason. I should also mention Project Reactor has timeout handling as well. The blocking get and blocking optional or block optional operators in these reactive streams frameworks are very similar to the join method in Java CompletableFuture that you've been doing and you did for programming assignment number 4. So once again, you try to limit these to just kind of one place if you can possibly avoid doing it anywhere else, which is a good thing to do. Okay, so that's the end of the discussion of blocking operators in the single class. Now let's turn our attention to the really cool part of assignment number 5, which is parallel processing with the ParallelFlowable class. And it's beyond the scope of tonight's lesson to talk about flowables in great detail. I have a bunch of other videos that talk about what a flowable does and how it supports back pressure. If we have time, next week we may go through some of that stuff because it is kind of cool and it is very germane for people using RxJava or Project Reactor for that matter in practice. But I don't want to delay giving you the knowledge necessary to do programming assignment number 5. So we're going to cover ParallelFlowable first without really going through the flowable in any detail. So basically what it does is it simplifies, by some use of the word simplify, parallel processing or concurrency relative to the flatMap concurrency idiom. So in the upper right-hand corner, we show the flatMap concurrency idiom, which is not the hardest thing in the world to deal with, but it's a little bit wonky if you're not used to it. Down on the left-hand side, we show the same approach, except using parallel flowables. And I think arguably it's more concise and easier to understand because it looks a lot like parallel streams. So let's talk about ParallelFlowable. First, we'll motivate it. So RxJava's flatMap concurrency idiom, which I outlined before, performs pretty well, but it's a bit convoluted because you've got to essentially write this inner logic that will take each item that's emitted from the previous operator and then subscribe it to run in the appropriate background thread pool, which once you understand the idiom is not the end of the world, it's just a little bit wonky. In contrast, here's how we get parallel computations with parallel streams. So here it is with the observable concurrency, flatMap concurrency idiom that we have in RxJava. Here's what it looks like with parallel streams. I think you would agree that parallel streams is much more straightforward. You take the array, you run it, you take the array, you run everything in parallel, you map everything and multiply it and reduce the results to add them all together. Very straightforward, no muss, no fuss, intuitive, nice and clean. So ParallelFlowable is a subset of Flowable that provides a more concise means to process multiple values in parallel. So as you can kind of see here, with ParallelFlowable, we have these things called rails. Just think of them as essentially threads in a thread pool. And the elements that are being emitted are mapped in a round-robin-like way onto those rails, onto those threads, and then those things run in parallel. And then there's a way to be able to convert the ParallelFlowable back into a sequential flowable to get the results and combine them in some reduced way. So this is very similar to Java streams, Java parallel streams rather. And it's intended for so-called embarrassingly parallel processing. And let me write something down here because I just saw a little glitch that I want to fix. 117. So 117, we will fix select to list. Okay. And I'm sure you remember, hopefully, at this point, what embarrassingly parallel means. It just basically means there's no dependencies or no communication between tasks. The other nice thing about ParallelFlowable is it avoids the somewhat convoluted syntax of the flatMap concurrency idiom, which is nice. There's a factor method on Flowable called parallel, much like there's a factor method on stream called parallel. And this takes a Flowable and makes it into a ParallelFlowable. So you can see here we had some sequential programming, some sequential emissions. We use parallel, we give it the rail count, which is like the number of threads you want, and then it goes ahead and maps the elements onto those rails. The elements are processed in parallel via these rails in round-robin order. There's really not too much that you can do to control this, but that's okay. It just takes them and runs them. By default, the number of rails is set to the number of available CPU cores, very much like what we saw with Java streams, parallel streams, where by default, you end up with a stream that runs with as many threads or as many threads in the pool as there are CPU cores. You can change the setting programmatically by passing in a parallelism count to the parallel factor method. Again, no real surprise there. So let's talk about some of the operators that come with ParallelFlowable. They're essentially a subset of all the operators that exist in Flowable. You don't get all of them, you just get some of them. Basically, the ones you get are the ones that lend themselves to parallel processing for embarrassingly parallel computations. So you can see here we have map, filter, concat-map, flatMap, collect, and reduce. We're going to use some of these methods, particularly map and flatMap, and I'm not sure if we use filter. We may use filter, but in a different place. So the main thing we're going to be doing is mapping and flat mapping. There's another thing you need to understand. Once you convert a Flowable into a ParallelFlowable by calling parallel, you also then have to specify what scheduler is provided to run the rail computations upon. And we'll talk more about schedulers in a second. Schedulers are a very cool way that you can parameterize parallel processing or concurrent processing with RxJava. Similar, if not identical concept, or not identical, but a very similar concept exists with Project Reactor. And schedulers can be parameterized. You can pass in different schedulers. And we'll talk about some of the ones that are matter, the ones that we're going to be using for our program, for programming assignment number 5, will be the IO scheduler, because, of course, these are IO-bound jobs. And downloading and processing and storing images has a lot of IO involved with it. And interestingly enough, the scheduler that is provided to ParallelFlowable's run on is not supposed to support work stealing, and that's because it uses this round-robin-like mechanism. Not really sure why they have that constraint, but they do. And what you get back from run on is a new ParallelFlowable instance that you can then apply those subset of ParallelFlowable operators on, like map and flatMap and so on. Now, once you're finished doing all the parallel processing, you can essentially convert your ParallelFlowable back into a good old-fashioned normal non-ParallelFlowable by using the sequential method. And this merges the values from each rail in a round-robin fashion. So they just all, whenever they're finished, they get stuck probably into a queue somewhere and will then be processable by later elements in the stream, later operators. There's other ways to be able to get the results of a ParallelFlowable back into something that's non-parallel, like a flowable. And you can use the reduce operator, and reduce can be used to do some operation to each element and then return a flowable as a result. So here you can see the reduce method will reduce all the values within a rail and across rails into a single flowable. And it takes a by function that reduces 2 values into 1 successively for each pairwise combination of items that are being processed. What you get back is a flowable that contains just 1 element. It's a little bit weird why they don't return a single. Honestly, not sure why they don't return a single, but they return a flowable that just has 1 element in it. So that's the overview of the ParallelFlowable class. Now, when you watch the walkthrough video for assignment number 5, you will see that it has a discussion in the specification comments of, I think it's maybe 3 different methods in RxFlowable crawler that are going to use ParallelFlowables. I think there's 3 places. It says it pretty clearly in the video and in the comments. So those are the places you'll have to use ParallelFlowable. If it doesn't explicitly require you to use ParallelFlowable, don't use ParallelFlowables. There's easier ways of solving the solutions for those different methods that do not require ParallelFlowables. Okay, so let's talk a bit about schedulers. Now, there's a lot of different schedulers. There's a compute scheduler called computations in the schedulers.computation factor method. There's single-threaded schedulers, not really useful for parallel processing, obviously, but could be useful for other things. We're going to focus on the IO scheduler. And as you can see here, that is obtained by calling the IO factor method on the scheduler's Java utility class. And what it does is it hosts a variable size pool of single-threaded executor service-based workers. And I don't know why they do their implementation the way that they do, but they do it in a wacky way. It does not use the IO thread pool, does not use any of the built-in Java common ForkJoinPool or fixed size pool or cache size thread pool. They have their own thing for whatever reason. And when you call IO, it returns a new scheduler that's suited for IO-bound work. In particular, it's optimized or it's amenable for use with blocking operations, so operations that block, which is fine. That's what we want in our use case. You could use it for compute-bound or CPU-bound tasks, but you're much better off using a scheduler that's designed for that, which would be schedulers.computation. The scheduler will either start a new thread or it will return an idle one from a cache of threads. It's obviously an implementation detail how that works, but that's what it does under the hood. And of course, as with any thread pool, well, not any thread pool, but as with most thread pools, the goal is to maximize CPU core utilization. That's really the idea, is to make things take full advantage of the underlying hardware as much as possible. Therefore, the IO scheduler is typically used for doing things like making networking calls, file input-output operations, database operations, things that might block on synchronizers, and so on and so forth. This particular example, which you can find in the EX4 case study in the Flowable folder, in the subfolder in the reactive folder, in my live lessons GitHub repository, is going to be used to download images from remote web servers in Parallel and store them on a local computer. So you can see here we get a bunch of URLs as a Flowable. We convert that into a ParallelFlowable. We run that on the IO scheduler. We download and store the image. At that point, everything is running in parallel. We then use sequential to turn it back into a sequential Flowable. We collect the results into a list and continue on. So that'll give you a hint kind of some ways to do this stuff. So that's basically what we're seeing here. And that's a nice hint as to how to structure your code. It's not identical to this, but it's similar in some ways. Under the hood, the thread pool that's returned from IO is implemented by so-called daemon threads, and they won't prevent the app from exiting even if its work isn't done. So if the main thread returns, then all the daemon threads will be destroyed in the most vicious and horrible way imaginable. And so just be aware of that. You don't want your main thread to exit without having everything else be finished. Project Reactor has a scheduler called bounded elastic, which is returned by the bounded elastic operator in the scheduler's Java utility class in Project Reactor, which works very much the same way as IO and the IO scheduler works in RxJava. Likewise, the Java ForkJoinPool is also very similar to these different thread pool models. When you use it with the managed blocker mechanism, if you don't use the managed blocker mechanism, then it's really intended primarily for computation-bound tasks. But if you use the managed blocker, then it works just fine as well. Okay, that's the end of the scheduler stuff. As you may have surmised, you'll need to use the IO scheduler in programming assignment number 5. So now we're going to talk about, I think this might be the last topic here, and this is a really fun one, and this is probably the most complicated part of trying to figure out programming assignment number 5 is the use of this composing operator. So this particular class of operators is used to make it possible to implement custom flowable operators. And the compose is the operator that we care about here. So the compose operator, and if you want to learn more about this, take a look at this link, how to implement your own operators in RxJava. So the compose operator transforms the flowable that it's called upon by applying a flowable transformer function that's passed as a parameter. So this composer function parameter, which is of type observable transformer, will be used to transform the current flowable. And it returns a transformed flowable. Actually, I should probably update this. This shouldn't say observable. It should say flowable. Let me write that down. I got to fix that too. It turns out that both flowable and observable have this method compose. So what I'm describing for one will also apply to the other. Obviously, the types would be different. You use the compose operator to define custom operators that can be chained together along with the standard RxJava operators. And here's a nice little article that is available on the web that talks about how to use the compose operator. Here's an example that we're actually going to look at in a second. I'll show you how this works, where we're going to make a flowable that will determine the exchange rate from British pounds to US dollars, and it's going to do the computation in the Java common fork join pool, which is kind of cool. And this will basically allow us to showcase the use of compose. So what we're going to do, as you can see here, is we want to run this computation in parallel. We want to find the best price. And then what we're going to do is we're going to use the compose method to have this particular operation run in the context of the common fork join pool rather than run in the context of, say, the IO pool or the computation pool that comes out of the box with RxJava. So we can control where this computation runs, and we do that by adding the compose method to essentially interpose what thread pool will be used. And I'll show you that code in a minute. You could basically think about compose as implementing the decorator pattern that adds a behavior to an object dynamically. By default, it doesn't operate on any particular scheduler. It just uses the one that comes from wherever the computation is running. And there's a method in Project Reactor called transform deferred, which works the same way. Now, something I should have put in here, but it hasn't been finalized yet. They're thinking about adding something similar to Java streams. I think they're called deferred or deferrable or something like that, which is basically the same idea. It'll allow you to define your own operators in Java streams, much like we can do with RxJava. Pretty cool. I think it's going through the Java working group process, and may it emerge at some point with enough support behind it to become a preview feature in upcoming versions of Java. So that's the end of the overview of composing operators in the Flowable class. And the last thing I want to show here is this case study that'll illustrate how to do this. And this case study is available here. This particular example is going to demonstrate timeouts. It does this computation a couple of different ways. I'm going to focus on the one that uses ParallelFlowables because that's what we care about. So let's comment out the other piece of the code so it'll just run that example. So here's ParallelFlowables. So what we're going to do is we're going to iterate for up to S max iteration times, which I think is 5. And we're going to emit a string that's going to instruct the rest of the program to find the best price in US dollars from London to New York. And then we're going to use the .parallel factor method to make this flowable a ParallelFlowable. And then we're going to go ahead and we're going to say, run this particular computation using the common pool flowable or the common fork join pool. And here's what this looks like. So common pool flowable returns a parallel transformer or something that works on ParallelFlowables. And it takes the flowable that was passed to it. It calls the run on method. And then it passes in as the scheduler, the common fork join scheduler to schedulers.from. So you can see here that it'll take that common fork join pool and make that the scheduler that this is going to run on. So we're basically making a little custom operator that will cause the computation to run on the common fork join pool. And we notice how we just stick this thing right here. I guess I should probably change that ever so much to say something like this. Convert the flowable to a ParallelFlowable, and then run the computation in the common fork join pool. So of course, there is no method called run the computation in the fork join pool. So we use compose so we can basically interpose or have our behavior stuck here with the decorator pattern. Then we're going to go ahead and find the best price. And that's just going to do some magic. We don't care what it does. That uses the map method. And then we convert that parallel computation back into a sequential computation. And you'll notice that we do this. We do two things in parallel. First, we're going to find the best price in parallel with determining the current exchange rate from British pounds into US dollars. Same basic idea here, except in this case, you'll notice that we don't use the compose operation. So in this case, we're going to do the following. just to be different, convert the flowable to a parallel flowable. And then we're going to run the computation in the CompletableFuture. So notice this time we directly used that method in line, whereas up here we used compose to be able to decorate the processing with that particular operation. But otherwise, it's basically the same. And then this gets into some other methods with RxJava we're not going to talk about at the moment because they're not part of the assignment, but they're cool. And what we can do is we can take these two futures. We basically end up with a flowable, which is essentially a future, to double and a flowable to double. Both those things are running asynchronously. We're going to zip them together, which is a little bit like the combine operation in in Java completable futures. And when both of these things are done, we're going to convert them, and convert is basically just going to do a price times rate conversion, because that's what we got, the price and the rate. And then we're going to print the results out. So when we run this thing, this is also showing timeout handling as well. So if the operation takes too long to run, then an exception is thrown. We catch that exception using some magic operators that are exception handling operators. And you can see here that in this particular case, it will sometimes throw an exception, sometimes it will complete properly, sometimes other things will time out, and so on and so forth. And so it produces the right results that we have expected. But the main thing I wanted to show you here was this idea of using compose in order to be able to combine to decorate the results so that you can stream them together in a flowable chain of calls.